Uh, okay, so hello everyone to today's seminar. We have Christoph Schürmann here joining us from the University of Bonn. Christoph is a final year PhD student under Professor Norbert Langer, and he's interested generally in the evolution of stars. He makes stellar evolution models, and particularly massive stars and how they evolve in binary systems. Today, he's going to talk to us about X-ray binaries in the massive star regime in the Small Magellanic Cloud. Take it from there, Christoph. Thank you.
Yeah, hello, and thanks very much for the nice introduction. So where are my slides? Here are my slides. Hope you can see them. And let's talk a bit of my work of the last month. So as Attila already mentioned, I work in the massive star regime. And why are we interested in massive stars in the first place? So the thing about them, these objects, they basically form the universe. For example, they are the key driving mechanism behind the matter cycle in the universe. They have the stellar winds and supernovae steer the ISM. Massive stars also are the most important site for nucleosynthesis. So we have supernovae, we have merging neutron stars, which also come from the massive star regime. And massive stars are also interesting to study for their own sake, as they produce powerful and spectacular phenomena like supernovae, pulsars, gravitational waves, and so on. And one of the most important facts about massive stars is that they live in binary systems. So we know that about 60, 70, maybe 80% of massive stars have a companion. So it's, for most of them, it's unavoidable to interact with a companion and make stellar evolution even more interesting than for the single star case. So 6 years ago, I guess all of you remember, the first gravitational waves were detected, and one of the paths to the sources of this is the massive star branch. And this cartoon shows you the typical evolution, what we believe leads to a gravitational wave merger. This is not the only option, not even from a stellar perspective. And this cartoon has many, many branches and dead ends and so on. So this is a huge simplification. But the key idea is that we start with two massive stars on the main sequence up here, go through a sequence of long living and short living, of easy to observe and not so easy to observe evolutionary steps, which end up here in the end in the gravitational wave merger of two black holes, two neutron stars, or mixed systems, which form a final compact object. As I mentioned, some of these phases are more long-lived, some are more short-lived, and this fact can be used to verify this evolutionary tree and to learn more about the life of binary stars and this whole pattern, how to get to gravitational waves, mergers, and so on, and all the interesting phases in between. So the most long-living and I guess best observed phase in this tree is the main sequence phase, where both stars are regular stars, where you can basically both of them see them either as two separate stars if they're close enough, or as a spectroscopic binary, where you have two absorption lines or emission lines, depending on the star, moving in a stellar spectrum. So this is, I would say, good, very good understood. But the more we get into this tree, into this path, it gets more and more difficult and more exciting. So if we have two stars sitting next to each other, we know that stars tend to expand during their evolution. And if there's a companion star, matter will, so the expanding star will at some point get in the gravitational regime of its companion, and matter will flow onto the companion, what we call Roche-Lob flow, which is the second image in this cartoon. And if this phase is stable, then we believe we get a system consisting of a helium star, so the naked core of the former primary star, the expanding star, and that the secondary star absorbed some of the matter of the donor star, and also that it accreted with this matter angular momentum and is now a very fast spinning star with the disk around it, which is observable as emission lines in the stellar spectrum. That's why we call them BE stars. E stands for emission. So this phase could be the next phase to look at when we want to understand this evolutionary path of the stars. And yeah, people did this. So we have, depending on the mass of the star, two different denominations for the helium star. We call them subdwarfs if they are rather light, and Wolf-Rayet star if they are massive enough to launch a thick stellar wind, which is observable by thick emission lines. However, the problem with this is that the subdwarfs, on the one hand, they are much, much dimmer than the companion star. So to observe the subdwarfs, it's quite hard. And so far, only about 20, 25 subdwarf plus B systems are known in the massive star regime. In the even more massive regime, we have the Wolf-Rayet stars, typically together with an O star. But the problem here is that the initial mass function of stars favors light stars. And so Wolf-Rayet stars are quite rare. And so it's also not very easy to do statistics with them. After this phase, we believe that the helium star explodes in a supernova. And after that, we are left with a system consisting of a complex object, so a neutron star or a black hole, together with a BE star, if the system did not break up during the supernova. And this type of systems down here, there we find objects like the X-ray binaries, supergiant X-ray binaries, stars with pulsars. In the lower mass regime, we find cataclysmic variables. We find stars with white dwarfs, and in the high mass end of the regime, we find stars, or may find stars with black hole companions. And the nice thing is this phase is well observable. So we know a lot of BX binaries. We know a handful of stars with pulsars, and we may or may not know stars with black holes, as I will discuss later in this talk. So we have some phases well observable, but these intermediate phases, which are very brief, they introduce uncertainty in this evolutionary path. So as I mentioned, we have the Roche-Lob flow and we have the supernova, and there are quite a number of unknown things happening. We have, for example, in case of the Roche-Lob flow, the mass transfer efficiency. So we don't know how much mass gets from the donor star to the accretor star, which ends up on the star. If all the matter gets onto the accretor star, we call this evolution conservative, if not non-conservative. And in case of non-conservative evolution, matter is lost from the system, and with this goes also angular momentum. But we don't know how much angular momentum is carried with the expelled matter. Another thing is the stability of this Roche-Lob flow. So is this flow of matter from one star to the other actually stable, or does the donor star expand so much that it gets to a runaway expansion and these two stars merge in the end? On the other hand, we have the reaction of the accretor to the inflowing matter. And it is believed that if the accretion rate gets larger than the thermal time scale of the accretor, then the star reacts by expansion, which may or may not lead to a stellar merger. And then the other short-lived phase, the supernova phase, there we know that there are supernova kicks happening, which induce randomness in the system. So even if you can describe properly the Rochavot flow, we get everything messed up again by the supernova kicks. So and since the supernova kick is distributed by some characteristic functions, we cannot calculate backwards from BX binary towards sums, because the supernova kick induced some randomness. So how are we going to tackle these uncertainties? For today's talk, I will leave the mass transfer efficiency as a free parameter, which I will vary throughout the talk today. For the angular momentum budget, I will make an assumption, namely that the material which leaves the system carries the same specific angular momentum as the accretor star. So this is a fixed number. Then we have the reaction of the accretor to the inflowing matter. And I will discuss this in the first half of the talk, how the accretor reacts to that. The stability of the mass loss of the Rochavot flow, this will be linked today to the reaction of the accretor, for which I found a nice mechanism to describe these two features in parallel. And lastly, we have the supernova kicks, which I will again treat as a free parameter. So another thing I will vary throughout the talk today. Next, let's talk briefly about my method. So I use a population synthesis approach to this. As I mentioned, we cannot trace back all the systems because we have so much based on random distributions. The thing with population synthesis is that it's possible to do this with detailed binary codes like MESA or BEC, but it's very costly. So it takes PhD thesis to run a whole grid of detailed binary models. So the solution which was developed in the past is to use rapid codes which look up the detailed properties of the stars from either fits or tables. So the code I use, which is called Combine, there we have tables for stellar evolution and interpolate the properties of the star from these tables. The thing with this solution is the details of the interaction get lost. So for example, if you have a star losing matter, it gets out of equilibrium, and this is not possible to model in tables. So therefore we have to do additional work, and our approach is to learn from selected detailed models. So run a controlled set of detailed stellar models, look into that and try to understand what is happening there to adapt this to a rapid binary population synthesis code. And as I mentioned, I decided to tackle the reaction of the accretor star. And so I ran a grid of stellar models with SMC metallicity because I'm interested in that galaxy, of different initial masses, which are with a constant accretion rate onto the star. And in the following diagram, you will see that there are two important timescales for this phenomenon. We have the thermal timescale of the star, also known as Kelvin-Helmholtz timescale, which basically describes how the star changes its structure. And we have the accretion timescale, so timescale related to the accretion rate onto the star. Good. Let's look at some results. So here I have a Hertzsprung-Russell diagram of an accreting stellar model. We have effective temperature on the x-axis, luminosity on the y-axis, and these gray lines running diagonally, they are lines of constant radius. And the black dashed line, this is the zero-age main sequence. And for this diagram, I selected stars of initial mass of 5 solar masses, which have their sums position here where my cursor is. And if we let them accrete better, depending on the accretion rate, they follow different paths through the Hertzsprung-Russell diagram. So in case of a low accretion rate, encoded in blue, the stellar model simply climbs up the main sequence until we reach some termination point. In this case, I stopped the calculations after the stars reach 25 solar masses. However, if we increase the accretion rate, you can see that the stars leave the zero-age main sequence and evolve at first shortly to the left, and then, this is the important thing, to the right. So they expand under accretion, and this expansion, you can see this here in the brown, pink, and gray curves, gets larger for larger accretion rates until this pattern breaks. You can see we have the largest expansion here in the gray curve, corresponding to 10 to the minus 3 solar masses per year, but the next two larger accretion rates, yellow and blue, they are not visible anymore because the calculation terminates early after the onset of the accretion, which we interpret as the star not be able to accrete such high inflow rates, getting so much out of thermal equilibrium that it in the end will lead to a merger. We can understand this interpretation better in the next diagram, where I show the radius of the stars depending on the current mass. So at first, let's focus on these dashed models here, which are the same as I showed before. We start at 5 solar masses and accrete until, in this case, we reach 10 solar masses to make space for the next couple of models. And again, you see with a higher accretion rate, we get a higher radii. And now we shift our focus from the initially 5 solar masses to the 20 solar mass models. And here you can see that we get a bifurcation. We either accrete steadily with an increasing radius, or after little accretion, the stellar radius basically diverges. So gets to huge radii after only accreting a fraction of solar mass, which formed our interpretation that if we have accretion rate which is too high, the star expands so rapidly that it swallows its companion, which in the end leads to a stellar merger. You can also see that this pattern of this bifurcation gets more intense with higher masses. So for the 50 solar mass star, here the green line, the radius barely changes. For the 5 times 10 to the minus 3 solar masses per year accretion rate, but just a little bit more intense accretion rate, 6 times 10 to the minus 3, then the stellar radius blows up, which may lead to a merger. we can collect all the stellar models in another type of diagram. This one where we have the initial mass on the x-axis and the ratio of the two time scales I introduced earlier on the y scale. So the ratio of the thermal time scale and the accretion time scale. And you can understand this diagram in such a way that in the upper part of the diagram there's high accretion, and in the lower part there is low accretion. And the color of the diagram indicates the increase in radius of the models. So here this blue purple hue means there's no radius increase, and if it gets close to yellow, then we have then the radius multiplies by 100 during the accretion. Models indicated in red are models which don't accrete stably, which we, as I mentioned, interpret as the models leading to a stellar merger. And the interesting thing is that we can separate these two kinds of models, the stable models and the unstable models, by two simple lines. Giving us one regime where we have moderate expansion, and one regime where we know a stellar merger happens. So this will be the in the future will become the description how I will decide when the accretor is stable or not. In the past, other assumptions were used. So I took two values from the literature, which was used in the past. So, for example, Schneider-Isert et al. They used a simple criterion by comparing the thermal time scale and the accretion time scale, and if the one is larger than the other, if the accretion, if this t is larger than 0, they decide, okay, we have the unstable case, this stars merge, or they lose matter in an amplified way. And in here below the line, they decided to have stable accretion. In contrast, Shao and Li, they moved this line to the value of 1, which is motivated by some works from the 70s. So as you can see, we've found a more sophisticated way to describe this process. So this is where I am now at my work. My next step is to implement this feature in the code. And so far I've used a simplified version based on all the stellar models, which is described by the blue line here, where we have roughly two regimes. In the low mass regime, there we have rather stable accretion, and in the high mass regime, rather unstable accretion. And on this model, the following diagrams are based. So at first, we can have a look at this diagram. So as I mentioned, I will treat the accretion efficiency of this binary star as a free parameter. And in the following, I'm going to work with this diagram. We have the accretion efficiency on the x-axis and the let's say the observations on the y-axis. So here we compare the outcomes of the population synthesis with the actual observed number of stars. So here a value of 1 means that the population synthesis yields the same number of a certain kind of star as observed. If we are above that, then I overpredict the kind of stars, and below one I underpredict them. make this more understandable, let's look at some curves in this diagram. So this blue line indicates now the number of BE stars in the Small Magellanic Cloud above a certain detection threshold, which is I think magnitude of 18. So you can see that for low accretion efficiencies, my code underpredicts the number of BE stars, but for high accretion efficiencies, I get into the right ballpark. The reason is, why is the number of BE stars increasing with higher accretion efficiency? It's basically an IMF feature. So if the stars accrete more, the more abundant low mass stars get pushed above the detection luminosity, and we end up with more BE stars observable. Next, let's have a look at the number of BE X-ray binaries in the Small Magellanic Cloud, in this case without a detection threshold. And here we see three cases for three different kick scenarios. For the dashed line, I should start with the dashed dotted line. There we have kicks following the Hopps distribution. The continuous line, in this case, I reduced the supernova kick for electron capture supernovae, and the dashed line, in the case of the dashed line, core collapse and electron capture supernovae kicks are reduced. And you can see that all the three lines are decreasing with high accretion efficiency. And the reason for that is that, if we put more matter onto a star, the companion star gets more massive, and therefore it burns its fuel faster, life and the life of the star is shorter. So the number of stars gets reduced. And you can also see the difference for the different kick scenarios. The reason behind that is if we reduce the kick, the systems stay bound. So if the kick is too strong, the two stars, the neutron star is kicked out of the system, and we don't have a stellar system anymore, but two single objects, a single neutron star and a single star. But if the kicks are reduced, it's more likely that the system remains bound, and that we have the neutron star orbiting a BE star yielding a BE X-ray binary. Then let's look at the magnitude, the V-band magnitude of the dimmest BE X-ray binary, encoded in green. But this time, it's the relevant numbers are on the other side of the diagram, where I show the difference in magnitude between my models and the observed value 16.9. And you can see again in the high mass, in the high accretion efficiency regime, I get a good agreement between observations and my calculations. For low accretion rates, accretion efficiencies, we see that since the stars don't accrete so much, my models remain dimmer, and therefore we have an offset here between the observed magnitude and the calculated one. So far for the what I would call low mass stars, BE stars. Let's go to really high mass stars. It's all high mass stars. So let's go to real high mass stars, Wolf-Rayet stars, the pink line, and you can see we get the observed number of Wolf-Rayet stars in this mass regime in case of low accretion efficiency, which is very interesting. So it seems like the accretion efficiency in Rorschach overflows depends on the mass of the stars forming the stellar system. And you may wonder, why is the number of Wolf-Rayet stars? And the binaries, if the binary companion is more massive, it lives shorter and blows up at some time, forms a supernova. So the number of Wolf-Rayet systems gets down. Okay, so far the numbers. Next, I want to show you the magnitude function, or I find. So and at first we will look at the B star regime. So here in this diagram, I calculated the V band magnitude for the stars I modeled, and I give you on the y-axis the number of systems. And we have two colors here, yellow and blue. The blue histogram, those are all systems which come out of my calculations after Rochlov overflow. So any kind, no restriction at all. The yellow population, those are all post-Rochlov overflow systems which consist of a star with a neutron star companion. Get a step further, here I indicate by black dots whether the star, the accretor of the Rochlov overflow became a B star in my model. So anything covered by black dots, those are B stars. So in case blue plus black dots means any kind of B star, and yellow plus black dot means neutron star plus B star, which is usually understood as B X-ray binary. And yeah, as you can see, this yields some characteristic slopes for the magnitude function, and we can compare this to observations. So here I plot the work from Schroedermeyer and Havel and Sturm. And you can see there's very good agreement between the models and the observations in Small Magellanic Cloud. You can see we find a matching slope. And as I already showed in the previous diagram, we also get the right numbers for BE stars and BX binaries. And as far as I know, we are the first group to get all of this matching. So from the same initial conditions, from the same run of the code, we can reproduce the numbers of BE stars, of BX binaries, and their magnitude functions. So this is a very nice success. You can see here at magnitude of 17, this is the detection threshold. So that's why the numbers are decreasing so much. And as I mentioned, this is optimized for the stellar mass regime of about 10 solar masses. So here in the high mass end, it's quite natural that here we have the discrepancies between models and observations. Okay, so it seems like I have 10 minutes left, so I'm going to show you some selected interesting diagrams. Maybe I'm going to show you this one. So here I show the orbital properties of my BX binaries. Period on the y-axis, eccentricity on the on the periods on the x-axis, eccentricity on the y-axis, and basically the number of systems is encoded in this hue. So black means they are the most systems. And above and right to the diagram, you see projections of this histogram. So in this case, this is a histogram for the eccentricity of the BX binaries. This is a histogram for the orbital period of the BX binaries. And here, this is a two-dimensional histogram where I show both together, eccentricity and orbital periods. And you can see the eccentricity profile is rather flat, with a preference for eccentricities above 0.2. And for the periods, you can see that I predict most of the orbital periods of BX binaries to lie between 10 and 100 days. And yeah, together in this joint histogram, you see in this corner between 10 and 100 days and below 0.3, eccentricity 0.3, they expect the most BX binaries to lie. And yeah, indeed, the observations follow these things. We have so most BX binaries have periods between 10, 100, maybe a few hundred days. And again, the eccentricities, they are quite low. So, whoops, my phone made some noises. Okay, so this is quite nice. And now we can move to the high mass regime. So a reminder, this is the diagram I showed earlier, and now we are here in the regime with low accretion efficiency, which we identified via the Wolf-Rayet systems as the accretion regime for, let's say, 30 solar mass stars. So typical for Wolf-Rayet stars and maybe for black hole progenitors. And at first, I want to show you the work of my bachelor student, results of a bachelor student, Vasco, who did a topic or a thesis on the Wolf-Rayet plus O stars, in this case, the Large Magellanic Cloud, because there we have more system observed. He found some very interesting things. So here on the left, you can see a diagram with the luminosity of Wolf-Rayet stars and the luminosity of the OB companion, so for systems consisting of a Wolf-Rayet and O star. And he qualitatively compared the observed distribution, shown in blue, and the luminosity distribution, which comes out of the simulations, shown in yellow. And the best agreement between these two clouds he found for a low accretion efficiency, as I found in the Small Magellanic Cloud. He also predicted some numbers. So in this diagram on the right, you can see the orbital periods of Wolf-Rayet plus some object systems, and this what I just called some object. Those are either OB stars, shown in yellow, or black holes, shown in black. And he managed to reproduce the right number of Wolf-Rayet stars, and also predicted that maybe 20 to 30% of the Wolf-Rayet stars in the Large Magellanic Cloud may harbor a black hole as a companion. Interestingly, he also predicted some small population of black holes very, very close to the Wolf-Rayet star, so with orbital periods of a few hours, of which we know or may know one candidate in the Milky Way, Cygnus X3, which could be the outcome of a so-called common envelope evolution. So this is very interesting results, and very promising that we may find black holes hidden in the vicinity of Wolf-Rayet stars. Turning back to the Small Magellanic Cloud, I'm going to show you some properties of the Wolf-Rayet, not the Wolf-Rayet, the O stars with black holes in there. So, for example, let's look at this diagram. These are the masses of OB stars and black holes, again shown in this 3-panel histogram. So we have histogram for OB masses here in the upper histogram. The black hole masses are on the right, and the joint histogram, the 2D histogram, where the hue indicates the number, it is shown in the middle. And as expected, the masses are skewed towards low masses because of the IMF. But the interesting thing in this diagram here is the number. So if you integrate this histogram here, you find that the total number of OB stars with a black hole companion in the SMC could be as high as 300, 350 systems. And for systems with a BE star with an emission line feature, these numbers could be 160. So I predict the Magellanic Clouds, the Small Magellanic Cloud, is a pretty nice playground to study black holes in the vicinity of stars. We can also enrich this diagram with some observations, not for black holes from the Magellanic Clouds, but from all the black holes we know or may know. So in blue, I indicated all the black hole plus high mass star systems I could find, and I also showed the SMC Wolf-Rayet plus OB systems in pink here, and you can see all these systems, they are located where my simulations are located. So this is a nice confirmation that my calculations could be on a good way. One grain of salt, we have, I also indicate the system MWC 656 down here. The BE star, which may have a black hole, this is under debate if there really is a black hole in the system, or if it's it may be in reality a subdwarf. So this is still not known. And one last diagram. Hope I'm not running out of time. I think that's okay if I show you a last diagram.
Christoph, you have 5 minutes, so.
Okay, then that's nice. Here I have the rotation velocity of the star next to the black hole on the x-axis, and the orbital velocity of the star on the y-axis. And you see that we have two populations of OB stars with a black hole in this diagram. We find one set of systems where the star rotates very fast, but the orbital velocity is rather low. And on the other hand, we have a population where the star rotates not so intense, but the orbital velocity is quite high. You can see that the high rotating stars correspond to BE stars, so indicated by white dots up here. And the stars with high orbital velocity, they are in general not BE stars. We can understand this by thinking about what is happening in the Rauschenbauer flow. If the systems close, then we get a high, if the system is close, we get a high orbital velocity. And if angular momentum is transferred to the equator star, then we would expect it is spun up by tides. But if the system is close, as I mentioned, the tides keep the equator star in co-rotation with the orbit, so it doesn't get high rotation velocities, doesn't become a BE star. On the other hand, if the system is wide, called case B Roche overflow, then tides are not efficient. The equator star reaches high rotation velocities, but its orbital velocities are low. And there's also some observations, and you see that they the few cases I could find and could manage to get orbital and rotation velocity, they indeed lie in the vicinity of the peaks in the populations I predict. But the key message of this diagram is that it may be fairly easy to identify systems with a black hole in the Magellanic Clouds. So I can give you two predictors. The first would be a massive star with a high rotation rate. There, it is possible that a black hole is around the star. Or SB1 systems, so systems with a high orbital velocity, where the companion star is not seen. So yeah, interesting task for the observers, I guess. Good. Then let me summarize. So I've shown that the accretion on main sequence star may be mass dependent, and that the reaction of the accretor also may be mass dependent. We've seen that I expect a rather high accretion efficiency for stars of, let's say, 10 solar masses, which yield B stars by extra binaries, and rather low accretion efficiency for higher mass stars, which lead to Wolf-Rayet stars and black holes and so on. I'm able to reproduce the numbers, number ratios, magnitude functions, period distributions, and so on. And I guess the most interesting feature I find is that I expect a number of roughly 300 OB plus black hole systems in the SMC, which could be relatively easy to observe. Observers, please correct me if I'm overstating this. So either we have a BE star, an emission line feature there, or we have an Wolf-Rayet SB1 system, spectroscopic binary with one line moving there. So yeah, we live in exciting times, and we may find lots of black holes soon. And with that, thank you for your attention.
Great. Thank you, Christoph, for a lovely talk. We'll take questions now from the audience, so feel free to start asking, please. Yes, Danny, please go ahead.
Hi, Christoph. Very nice talk. Thank you. Regarding the number of the predictions on the Wolf-Rayet stars in the SMC, where you seem to show that the low accretion efficiencies are valid. There aren't that many Wolf-Rayet stars in the SMC, though, are there? I mean, they're less than 10. I'm trying to remember the number, but I can't.
Yeah, indeed. It's of the order 10. I think it's 9. Indeed. I hope I mentioned that. So for the Wolf-Rayet stars, the uncertainties for this model, they are relatively high.
Yeah, I mean, it would be interesting to see how that holds up for the LMC, whereas you've already said you've got many more Wolf-Rayet stars. It just seems a bit weird to me that the difference is so is so emphatic there.
Yeah.
Is there any physical reason why you would expect that? I mean, the efficiency, the mass accretion efficiency is much lower in the Wolf-Rayet plus black hole denote star.
So two ideas are in the room. It could be related to the luminosity. So in the high mass regime, the stellar luminosity, the radiation pressure could keep the material away from the equator, or it could be linked to stellar winds. But to give a definitive answer, we have to do more modeling.
Okay, thank you.
Thank you, Danny. Anyone else? Sergio, yes, please.
Yep. Can you hear me?
Yes, we can hear you.
Okay, so thank you very much, Christoph, for this very nice overview of what model says. I have one comment and one question, curiosity. The first thing is that I think it's a bit kind of dangerous to use this term B or OE for those stars that are rotating fast due to this interaction. Because from the observational point of view, we see that not all fast rotating massive stars are OE-BE. So I understand what you mean by that, but maybe for the community that is not working on this can be a bit confusing. So I don't know, maybe using the E in brackets, saying that could be an emission line star, but not necessarily.
Yeah, that's a good point. Thanks.
So this is one just clarification, but then the important thing is my question. So we found that if you go to the last diagram that you have shown with the Vicinai, the rotational velocity versus the amplitude. So there is something that we have found from the observational point of view is that in the fast rotating tail, many of the stars are runaways. So even if this star, maybe they were before a black hole, O star, B star plus a black hole, maybe during the supernova event, this was disrupted. So I was wondering if you have a way to have some idea from the computation if the binary is going to be disrupted or not, because this is important when we will begin to compare the statistics of what we observe with your predictions. Some of these systems are going to be, the black holes are going to be kind of floating.
Indeed. We expect that there is some relation between these two variables I show here. Oh, no, not the orbital velocity, of course, and the runaway speed. We also made some diagrams. I don't have them here. But yeah, we are looking into this, and if I remember this correctly, it's follows the pattern you mentioned, that the rotation rates are linked to runaway stars.
So you think that there's a way to kind of in your computations say, or to know if the binary star after the explosion and leaving the black hole is going to be disrupted, or is something that is not easy to take into account in the computation, is not easy to be predictable?
We can predict that. We can also predict the runaway velocity.
Okay, now I see.
So if this is project is finalized, this will also be included, I hope.
So this is great. Sorry.
Yeah.
Thanks.
Thank you, Sergio. Anyone else? Okay, Christoph, I have a couple of questions.
Yes.
So if we just go back to the histogram plot that you showed, which had two histograms in it, OB stars with neutron stars and the ones which have no or other companions. Yes, prior to this? Yes, I suppose also this. So the blue histogram, exactly what does that include? Which systems are they exactly?
Any kind of systems after Roche overflow. So could have a white dwarf companion, sub-dwarf companion. so anything which anything. So I plotted this to be combined with the BE star predictor, the black dots here, to predict the number of BE stars.
Okay.
Is this clear?
Well, I was just wondering, what does no companion mean? So, I mean, these are all binary systems, no?
Yeah. If the system broke up after a supernova, if the supernova kick removed the companion from the system.
Understood. Okay.
Okay.
And the other question was going back much earlier when you showed us those plots with the different accretion rates, and you showed us the HR diagram.
This one.
Yes, that's right. So under what initial binary parameter space can we get such high accretion rates?
So this I didn't check this actually. So or what do you mean? So this is not related. These models, they are not binary models, they are single star models.
Yes. So what I'm trying to understand is in a realistic binary model, what would be, for example, the masses, the orbital period and mass ratio initially of the system to realize these very high values of accretion rates?
Depends on the accretion efficiency. This is the I would say the key feature. From the top of my head, I don't know the like periods and masses.
Okay.
I had to look this up. Sorry.
That's okay. All right. Okay. Yeah, because if we have to, we would also like to know the progenitors of these systems from binary models as well, right? So we need to know where we can get such high accretion rates. What should be the initial binary conditions for that? That's why I asked the question.
Yeah. So for my work, this your question wasn't let's say important, because so the idea was to cover the whole space. To see from where do we have the first reaction of the star to accretion to the breaking point.
Okay, perfect. Okay, thanks.
You're welcome.
Any other questions from the audience? No? Then great. Let's thank Christoph again. And that will be all from the seminar deck. Thank you very much for joining in.